Making the dry electrode process work at scale, which is a major breakthrough in lithium battery production technology, was incredibly difficult. If the dry electrode truly represents a breakthrough of this magnitude, why did Tesla wait more than 4 years after Battery Day 2020 to confirm mass production? And if the cost, energy, and footprint advantages were already obvious on paper, what forced even Tesla, the most aggressive risk-taker in the electric vehicle industry, to delay commercialization again and again? The answer is uncomfortable but simple. The bottleneck was never chemistry. It was manufacturing precision under industrial pressure. When Elon Musk says scaling dry electrodes was incredibly difficult, he is not referring to a theoretical limitation. He is describing the simultaneous optimization of cost, energy consumption, throughput, and statistical reliability at a scale of millions of battery cells per year. In traditional lithium-ion manufacturing, electrode coating and solvent drying alone account for roughly 30 to 40% of total factory energy consumption. Dry electrodes eliminate N-methyl-2-pyrrolidone solvent entirely, along with the massive drying ovens that can stretch over 80 meters per line. At Battery Day, Tesla estimated that dry coating could cut electrode stage energy use by up to 70% and reduce total battery factory capital expenditure by 20 to 30%. In a 100 gigawatt-hour plant, that translates into hundreds of gigawatt-hours of electricity saved annually. Real money, not marketing slides. Energy density improvements follow directly from binder reduction. Conventional wet electrodes typically require 5 to 10% binder by mass to maintain mechanical integrity after solvent evaporation. Tesla's dry electrode process reportedly operates at roughly 1.25% binder content. That freed mass is replaced by active material, enabling a 5 to 10% increase in cell-level energy density without altering the underlying electrochemistry. In a 75 kilowatt-hour battery pack, that improvement equates to an additional 4 to 7 kilowatt-hours of usable energy, or a 20 to 30 kilogram reduction in pack mass. Cycle life gains are equally tangible. Patent disclosures and internal test data suggest dry electrodes can retain around 90% capacity after 2,000 charge cycles under standard conditions, at an average consumption of 250 watt-hours per kilometer. This corresponds to roughly 800,000 kilometers of use, far beyond the realistic service life of most vehicles. The mechanism is mechanical rather than chemical. Solvent-free mixing reduces particle fracture, microcrack formation, and long-term electrode degradation. If the benefits are so compelling, why did Tesla hesitate? Because none of these advantages matter if manufacturing yield collapses. A modern wet coating lithium-ion factory typically requires yields of 95 to 98% to remain economically viable. Even at that level, battery production is capital-intensive and margin-sensitive. Early dry cathode lines reportedly struggled to exceed 60 to 70% yield. At those levels, scrap rates overwhelm every theoretical cost saving from solvent elimination. Rework, recycling, downtime, and warranty risk erase the economic case almost instantly. This is precisely why contemporary Amperex technology company Limited founder Robin Zung once described dry cathodes as impossible, not because physics forbids them, but because the statistical consistency required at automotive scale exceeds what conventional production control systems can manage. Tesla recognized this reality early and chose silence. Tesla did not delay because dry electrodes didn't work. They delayed because they refused to declare victory until failure probabilities were statistically suppressed. In the automotive industry, a defect that emerges after 6 to 12 months in customer vehicles is more dangerous than thousands of cells scrapped inside the factory. Warranty risk, recall exposure, and brand damage cannot be offset by theoretical efficiency gains. This is where Tesla's real advantage emerges. Contrary to popular belief, Tesla did not invent dry electrodes. Solvent-free coating variants have existed for decades in niche applications where volumes were low and economic demands modest. The challenge was never chemistry. It was mechanical control at extreme scale. Nickel-rich cathode materials are hard, angular, and abrasive. Binder distribution tolerances are narrow. Roller pressure must be controlled within a few percent. A particle size distribution shift of just 3 to 5 microns can trigger microcracking. A 2 to 3% deviation in compaction pressure can collapse cycle life below automotive standards. These defects do not appear immediately. They surface months later under real thermal and electrical stress. For a car maker, that risk is unacceptable. Tesla's breakthrough was not a new material, but a new manufacturing philosophy. The Austin 4680 production line does not operate like a traditional battery factory. It behaves more like a high-speed data center with chemical output. Every meter of electrode generates continuous streams of process data, pressure gradients, shear forces, density variation, and microcrack probability. Defects are no longer detected at the end of the line. They are predicted upstream, before an electrode becomes a cell. This approach relies on real-time statistical machine learning, computer vision, inline X-ray density scanning, and artificial intelligence-driven feedback loops that dynamically adjust roller behavior. Yield is not inspected into existence, it is trained. This system only works at Tesla's scale. A startup cannot afford the scrap required to train such models. A supplier lacks the vertical integration to close the data loop. A traditional original equipment manufacturer cannot endure years of negative margins during the learning phase. Tesla accepted all three constraints simultaneously and survived. By Q4 of 2025, a critical threshold was crossed. Dry cathode yield moved into the 90 to 95% range, where manufacturing economics flip decisively. At scale, each 1% yield improvement reduces battery cost by approximately $1 to $1.5 per kilowatt-hour. Scrap rates fell below economically damaging levels. Capital depreciation normalized. Production flow stabilized. Warranty risk became manageable. Only then did dry electrodes become real. Not a concept, but an industrial weapon. Tesla's decision to deploy 4680 dry cathodes first in the Model Y long range was not conservative. It was confident. The Model Y is Tesla's highest volume platform. High volume means fast feedback, massive datasets, and immediate exposure of any weakness. If dry electrodes had unresolved reliability issues, this is where they would surface first.